titanium monoxide has a rock salt structure. X-ray diffraction data shows that the length of one edge of the cubic unit cell for titanium oxide, where the ratio of titanium and oxygen atom 1:1, and the edge length is 4.18 angstrom, and the density as determined by volume and mass measurement is given 4.92 gram per centimeter cube. So this is the experimental value. So from all this data, we have to find out whether there is any defects present or not, and if defect is present, is it vacancy defect or interstitial defect, that you have to find. Titanium atomic mass is given 47.88 U. The presence of vacancies, that is Schottky defect, at titanium and oxygen sites, if it is present, then there must be lowered measured density. So this density that is given here, this is actually experimental, but from the formula of density, if we calculate the value, if that density, that is theoretical density, higher than this 4.92 this value, then obviously that proves that there is presence of vacancies. Okay, so there is density difference if Schottky defect is present. So it will prove after, when we will do the calculation of density, if the value is higher than 4.92, it will prove there is vacancy defect, and it must be Schottky defect, because we know that in Frenkel defect there is no change in the density, but in Schottky defect, after the defect formation, there is decrease in density. Okay, so now we will find out by using the formula of density, that is Z equal to density equal to Z into molecular weight and then divided by A cube by N. So this is the formula for density. Now as this structure is rock salt structure, that is for NaCl type of structure, for NaCl type of structure, the Z value, that is FCC type, so it will be 4. Okay, so we have written 4 here, and in place of molecular weight we have to consider Ti and O. So for titanium 47.88 and for oxygen it is 60. So we have to add these two values so that we can get the molecular weight of the crystal. Then we have written here A cube. Now A cube is 4.18 angstrom, but we have to change it to centimeter unit. Okay, because here 4.92 it is given in gram per centimeter cube. So we have to compare, so unit must be same. So 4.18 into 10 to the power minus 8, now it is in centimeter to the power cube and Avogadro number. So now from this formula, the value of density that we have obtained is 5.8 gram per centimeter cube, which is greater than this value, that is the experimental value. That means this is the density that should be present, but actually it is present, that is practically 4.92 is the density. That means density is decreased, so there must be some defect. Now this defect, so the first question we have obtained the answer. Do the data indicate that defects are present? Yes, the data indicates defects are present. And the second question, if defects are present, is it vacancy defect or interstitial defect? So the data indicates defects are present, and because the overall composition of the solid is titanium oxide, and it is also written here that it is 1:1 ratio. That means there must be equal number of vacancies of cation as well as anion sites. So that means it will be Schottky type of defect. And we also know that even if we do not consider this fact that equal number of vacancies, then also it will be Schottky defect, because Frenkel defect there is no change in measured density and theoretical density. So there is defect present. That is the first answer to the first question, and the second is it is vacancy defect, not interstitial defect. That means it is Schottky defect, it is not Frenkel defect. Okay. Next question, what type of crystal defects is indicated in the diagram given below? So here we have a diagram where we have Na plus cation, Cl minus anion. Now here you can see there is a vacancy of Na plus, another vacancy of Na plus, and here we have Cl minus vacancy, this is also Cl minus vacancy. So the vacancy of sodium plus and Cl minus, this ratio is basically 2:2. That means 1:1. Now this type of that is equal number of cation and anions are missing. That means here the ratio of cation and anion that will remain same. So this type of defect we have to choose from these 4 options, and it is Schottky defect, because only in Schottky defect the ratio of cation and anion do not change, because when there is one cation missing there is also one anion missing, which is clear from the picture here. If NaCl is doped with 10 to the power minus 3 mole percent of SrCl2. So from the question, first of all we have to understand what type of defect here we have. So this defect is basically, remember, it is impurity defect. So NaCl is doped with 10 to the power minus 3 mole percentage of SrCl2. So we are adding completely foreign material. So that is why it is impurity defect. And we have to find out what is the concentration of cationic vacancies, because we are replacing Na plus with Sr2 plus. So there must be some cationic vacancies, and we have to find out the concentration of that cationic vacancies. So here the calculation will be, we are doping NaCl with 10 to the power minus 3 mole percentage of SrCl2. That means what? It is percentage. That means 100 moles of NaCl, it will be doped with 10 to the power 3 moles of SrCl2. So 1 mole of NaCl will be doped with SrCl2 10 to the power minus 3 divided by 100 mole. That means 10 to the power minus 5 mole. So 1 mole of NaCl, there is presence of 10 to the power minus 5 moles of the impurity, that is strontium chloride. Now as each Sr2 plus ion creates one cationic vacancy. Why? Because basically 2 Na plus is equivalent to 1 Sr2 plus if we consider the positive charge. So that means when one sodium, it is replaced by Sr2 plus, another sodium plus that will also be vacant. Why? Because we have to maintain the positive charge before and after adding the before adding the impurity and after adding impurity, the positive charge must be same. So that is why as each Sr2 ion creates one cationic vacancy, so the number of Sr2 plus ion and the number of cationic vacancy both will be same. So the concentration of cationic vacancy, that will also be 10 to the power minus 5 mole per mole of NaCl. So for 1 mole of NaCl there is 10 to the power minus 5 moles of cationic vacancy. So this is the cationic vacancy in terms of mole. But if we want to convert it actual number, then what we will do? We then multiply 10 to the power minus 5 with Avogadro number 6.023 into 10 to the power 23. Now we are getting the actual cationic vacancies that are present per mole. Okay, so this is the concentration of cationic vacancies, and this is impurity type of defect. Radius ratio rule. So what is radius ratio rule and why it is important, that we have to know. Now when we consider array of anions present in the form of cubic closed bracket, so there are two types of holes that we have seen. One is tetrahedral type of holes, or it may be octahedral type of holes. Now octahedral holes are obviously, the space is more compared to tetrahedral holes, but these tetrahedral holes in different types of crystal, it will be different. So size of tetrahedral holes may vary, and size of octahedral holes, that may also vary depending on the crystal. Okay, now when the tetrahedral voids, the size will vary. Obviously the cations that will occupy these voids, that will also, that is cation size, obviously not same, crystal to crystal cation size will differ. Okay, so that means tetrahedral holes, that size is also changing. Cations will occupy the voids only if they are perfect space to accommodate them. So the size must be optimum. Okay, So this prediction of whether the ions will be able to hold the cations, that is whether the holes, tetrahedral holes or octahedral holes, these are perfect for the cation, that we can do on the basis of radius ratio. So this is the importance of radius ratio. So if we know the radius ratio, which is nothing but the ratio of the R plus divided by R minus. R plus is the radius of cation, R minus is the radius of anion. So there are some specific values. So if it falls in the particular range of radius ratio, then we can predict what type of structure we can expect. So this rule states that as the size of a cation increases, that means more anions of a particular size can be arranged around it, because now surrounding the cation the surface area is high. So higher number of anions we can arrange surrounding the cation. Okay, thus knowing the size of the ions, we should be able to predict a priori which type of crystal packing will be observed. So if we know the size of cation and size of anion, we will be able to predict the type of crystal. Radius ratio refers to as the ratio of smaller ionic radius. Now smaller ionic radius, this is obviously of the cation, by the ratio of larger ionic radius, which is anion. So radius ratio is basically R plus divided by R minus. So R plus is the radius of the cation, R minus radius of the anion. Okay, so if we know these two values, we can easily find out the radius ratio. Okay, limiting radius ratio. So here we have a picture. So if we look at this picture, there are three pictures basically. So when the anions are larger in size and surround the smaller cation, they are arranged in space such that anions and cations touch each other and produce maximum stability. In the first case, if we consider the space which is created by 4 anions, this space is larger compared to the size of the cation. So this type of structure will be unstable. Why? Because the cation, it is not perfectly fitted, so it can easily escape, it can easily slip out of the void. Okay, so that is why the structure is not stable. In the second case, the size of the cation and the size of the void, it is perfectly same. Okay, so it is optimum. So that is why we are calling it stability limit. So this is the perfect size. If the cation is lesser than that, it will be unstable. But what is the case if the cation is larger than this size? Suppose the cation is like this. Now when the cation size is increased, now look at the third picture. When cation size is increased, here also we have 4 anions, but they are not touching each other. Okay, but this is also stable. And here another fact is that this is simply 2-dimensional picture. But suppose if we consider 3-dimensional pictures, then another anion we cannot fit directly above it, because it is completely surrounded by 4 anions. So there is no extra space so that we can arrange another anion upper side and lower side. That is not possible. But in case of the third one, that is in this case, we can place anion over it and below it. That means here coordination number will be 6 and here coordination number maximum can be 4, not more than that. Okay, so higher is the size of the cation, higher number of anion we can arrange around it. Though from this picture it seems that in both cases number of anions are same, but if you imagine in 3 dimension, in case of this second picture, we cannot place 2 more anions above and below, but in the second case, the third case, we can place 2 more. So coordination number will be 6. Okay, so limiting radius ratio means basically this condition, that is the minimum value of radius ratio to have particular coordination number. Okay, so limiting radius ratio is the minimum allowable value for the ratio of ionic radii for the structure to be stable. So if the value is less than that, the structure cannot be stable. Okay, so that is why you are calling it limiting radius ratio. So this table is very important. Here we can see that when radius ratio is lesser than 0.155, basically coordination number is 2. Examples under this condition is not present because it is simply linear. Type of void is linear. Okay. So mostly important is these three. Fine. So 0.155 to 0.225, it is coordination number 3, triangular planar. Example is B2O3. But most of the time you will find examples from these three categories. Okay. So when it is 0.225 to 0.414, then coordination number is 4 and the type of the void is octahedral. Then the next range 0.414 to 0.732. Okay. Gradually the ratio is increasing and the coordination number, that is also very high. So basically this ratio is increasing means what? That means if we consider numerator and denominator, obviously numerator is becoming gradually higher and higher. Now that means the cation size is becoming higher and higher, and when cation size is high, coordination number will also be high, because now larger number of anions we can arrange surrounding the cation surface. Okay. And when coordination number 8, this is the value, and here type of void is cubic. Examples are given. Sometimes if you some problems, it is mentioned as that the structure is ZNS type. That means there will be coordination number 4 and type of void is tetrahedral. Sometimes it is said that the type of the crystal is NaCl type. So it is nothing but it means that it is of octahedral type and coordination number is 6. So these three examples are mostly used: ZNS for coordination number 4, NaCl for coordination number 6, and cesium chloride for coordination number 8. Okay. So here we have some examples. So beryllium sulfide, this is the ratio of cation and anion 0.59. See, the cation size is always smaller, and this is the size of sulfide, and it is 0.32. That means if you look at the previous slide, 0.32, it falls under which category? It is the third category, that is coordination number 4. Then for NaCl, the value is 0.56. Now 0.56 means it falls between 0.414 to 0.732, coordination number 6. And for CaCl, it is 0.93. So it falls in the 0.732 to 1 range. And in case of ZNS, again we are getting 0.4. That means it is also coordinate, just like beryllium sulfide, it is having coordination number 4. And you can also compare, I have given here this table so that we can compare here simultaneously. Okay. So BES 0.32, it falls in this zone. For ZNS also 0.4, it is in this range. For NaCl 0.56, between this range, and for CaCl the range is 0.732 to 1. Okay. Now we will solve the problem. If a solid A plus B minus has a structure similar to NaCl, that means octahedral void, coordination number 6. Consider the radius of the anion as 250 picometer. First question, find the ideal radius of the cation in the structure. Ideal radius of the cation. So basically we have to find the radius of the cation. So and the second question is it possible to fit a cation, any cation C plus of radius is given in the tetrahedral site of the structure A plus B minus? This is the second question. So we will take help of this table, and here first of all we will find out limiting radius ratio. So limiting radius ratio, smaller by capital R, this is nothing but R plus by R minus. So R minus, that is the radius of anion, that is expressed by capital R, and radius of cation expressed by small r. So this limiting radius ratio, we have taken this value, that is 0.414. Find the ideal radius of the cation in the structure. Okay. So here small r that will be equal to 0.414 into R, and small r is given 250 picometer. So these two, if we multiply, we will get the value of cation, which is 103.5 picometer. So this is the ideal radius of the cation in the structure. Okay, because in NaCl structure, the limit is starting from 414. Okay, so when we are using this value 414, we are getting 103.5. But if we use 0.732, that is the upper limit, then this value will be obviously more than this value. So that means this is the limiting value. This is the minimum value of cation that is possible. Okay, and if we use the another value, that is 0.732, then we will get the maximum value of the radius that is possible. Now come to the second question. Is it possible to fit a cation C+ of radius 180 in the tetrahedral site of the structure? So R by R, that is the radius ratio, R plus by R minus. For tetrahedral site, it is 0.225. Now for tetrahedral, this is the limit, that is lower side, this is the limit. So the R value, that will be 0.225 into capital R. That means capital R is 250 picometer, that is given. So here the value of the cation is 56.25. Okay, but here the value is given 180 picometer. And another way we can find out that if we consider R by capital R as 0.414, then the size of cation will be capital R into 0.414, which is nothing but this value, 103.5. So for tetrahedral site, this is the minimum size of the cation that is possible. For tetrahedral site, the maximum value of the cation that is possible. But if you consider this 180, it is not falling in this range. So cation size minimum is 56.25 picometer, maximum is 103.5 picometer. But 180 is far greater than that. Okay, so that is why the ideal radius for the cation in the given structure will be 56.25 for minimum, and maximum also we have calculated 103. So this means that radius of C+, it is very high than compared to 56 and also compared to 103. So it is not possible to fit cation C+ in a tetrahedral site. Okay, so this is the second answer. This is the first one, this is the second one. Another problem, in the octahedral structure, cation in an AB type solid have a radius 75 picometer. So here R plus is given. What will be the maximum value and minimum value for the size of anion filling the voids? So AB type of solid and octahedral structure, that is already given. So if it is octahedral structure, the range should be 0.414 up to 0.732. Okay, now R plus is given. So how we will calculate? R plus by R minus, it should fall in this zone. Now when we want the minimum value of R minus, so we will take R plus by 0.732, because when the denominator is high, then obviously R minus, it will be smaller. Okay, so that is why it is the minimum value. And when we want to get the maximum value of the anion that is possible, now we have to take this lower limiting value, that is 0.414, because now the denominator is minimum, so R minus value will be maximum. So this is a minimum value and maximum value. Okay, in this way we can calculate. Next problem, radius of AG plus and I minus both are given, 126 and 216 picometer respectively. So we have to find the coordination number for AG plus R. Now this is very simple. We just have to calculate R plus by R minus, that is the radius ratio, and from the radius ratio, whether it is falling in this zone or in this zone, depending on that, we can easily understand what should be the corresponding coordination number. So here R plus by R minus, this is 0.583. So it falls in which zone? It is falling in this zone. That means the coordination number will be 6. Coordination number is 6. Fine. So correct option will be option C. A solid AB has NaCl structure. That is given. NaCl structure means octahedral void, coordination number 6. Radius given 120 picometer. We have to find out the maximum possible value of the size of anion. Okay. So R plus by R minus, this must be in the zone of 414 to 0.732. R plus is given 1 to 0. So R minus will be, if we want to get the maximum possible value for R minus, we must take this value, because R plus then will be divided by 0.414. That means 1 to 0, 0.414, and that should be equal to 289.5. Okay. So it is matching with which option? It is matching with, not it is exactly matching, but it is closely matching. Okay. It is closely matching with option D. So option D will be the correct option. Remember, it is asking maximum value. That is why we have taken this lower value. But if it is asking minimum value, we have to take this value, because denominator then it will be high. Denominator high means R minus will be less. Okay. So table is also given for convenience. Okay. Sorry, it is writing it again. R plus R minus, we will take 0.414. So R minus will be R plus by R plus is 1 to 0, and this is equal to 289.9. So this is the correct option. Next we have assertion reason type of question. So in this question, assertion is saying that its sodium chloride crystal, each sodium ion is touching 6 Cl minus ions, coordination number 6. But these 6 Cl minus ions do not touch each other. Okay. And the reason is saying the radius ratio, that is R radius of Na plus divided by radius of Cl minus, this is greater than 0.414 required for exact fitting. So we have to choose whether 1, 2, 3, 4, which one of them will be correct. Okay. Now try to remember this picture that we have already seen. So in this case, the anions are touching each other. But in the second case, anions are not touching each other. Fine. So this is the limiting case, and this is not the limiting case. And here it is said that at surrounding sodium ion there are total 6 Cl minus ions, but these 6 Cl minus ions do not touch each other. So we have to consider this picture. Now when it is not touching each other, that means for NaCl structure we have to consider this range. Okay. Now if it is touching each other, that is anions are touching each other, that means it is the limit. So this must have value 0.414. But as it is not touching each other, that means now the size of cation is bigger. As the size of cation is bigger, now the value will be more than 0.414. Okay. So in the reason, what is written? Radius ratio is greater than 0.414 required for exact fitting. So the radius ratio is not 0.414, it is greater than 0.414. So this is actually the correct explanation for this observation that anions are not touching each other. That is the second case. So reason is correct, assertion is also correct, and the reason is the perfect explanation for the assertion. So which option we should choose? Both A and R are correct, and R is the correct explanation for A. Okay. Next we are starting, it is a completely different thing. It is the different types of properties of solid materials. Okay. There is electrical properties first, there is also magnetic property, dielectric property, etc. But we are starting from electrical property. So electrical conductivity, there may be different types. Okay, so we can categorize it in two types. One is electronic conductivity. So here basically electrons or positive holes are responsible for electrical conductivity. But in the second case, when we are saying that it is ionic conductivity, so obviously now ions are responsible for this conduction of electricity. Okay, so in case of first, that is the example mostly are metals, because we know in metals there are free electrons. And if we consider ionic conductivity, we can observe the corresponding example should be electrolytes, because in electrolytes there is ions. Fine. Now electronic conductivity, we can further divide it in two types. One is when it is conduction through electrons, because we have already written here that it is possible through electrons as well as through positive holes. So when it is through electron, it will be N type, and when it is through positive holes, it will be P type. Okay, so N for negative, in this way you can remember electron, negative, N type, positive, P, so we are calling it P type. In this way we can remember easily. Now electrical properties of solids, the previous classification that we have seen, that is on the type of electrical conductivity. Now depending on how much conductivity is possible for the solids, there are three types of the solids. So solids exhibit a varying range of electrical properties. There is a range. Okay, so this range is basically 10 to the power minus 2 to 10 to the power 7. Now the solid, there are different types of solids, and what is the amount of their this magnitude, depending on that we can classify them in three types. Okay, so try to understand the difference. The previous flowchart that we have seen, that is how many different types of electrical conductivities are possible, and here we will see what are the different types of solids for which are showing different types of conductivities. Okay, some are showing higher conductivity, some are showing lower, some are showing moderate. So conductor, very high conductivity, so this is the limit. Okay, so it is 10 to the power 7, 10 to the power 4, this is the range, ohm inverse, meter inverse. And for semiconductor it is intermediate conductivity, that is 10 to the power minus 6 to 10 to the power 4. So now see, this is the limit for high conductivity. Now from this limit gradually we are moving towards lower value. So 10 to the power 4 to 10 to the power minus 6, this range is lower compared to this range. Okay, and for insulators it is further reduced, it is 10 to the power minus 20 to 10 to the power minus 10. So this is very small, so that is why we are calling it insulator. Okay, now this difference in conductivities of conductor, semiconductor, insulators, how we can describe it? I mean, why there is difference in their conductivities, why they are not behaving equally? It is because of the band. It is can be described on the basis of band theory. Okay, so band theory can explain why conductors have maximum conductivity and insulators have minimum conductivity, and semiconductors it is in between conductor and insulator. Okay, so band theory we have to understand. What is energy band? When there is group of discrete but closely spaced energy levels. So suppose there is energy levels, they are very close to each other. That means closely spaced. So closely spaced energy levels for the electrons in a particular orbit, they will be called energy band. Because they are so closely spaced, we cannot individually see the levels as if it will be merged together. So that is why now it is appearing as band. So we are calling it band. Okay, not energy level, because now the levels are merged together. The energy band, which includes the energy levels of valence electrons. Okay, so for the valence electrons there will be a particular energy band, so that band will be called valence band because it is containing the valence electrons, and the energy band above the valence band, okay, just above the valence band, that will be called conduction band. Now when there is no external energy provided, the electrons obviously will reside in the valence band because that is their actual position, they should stay there. Now in case of conductor, as this gap, you can see this conduction band, this yellow zone and this is the blue zone, they are completely together, merged with each other, so the gap is very low. So that is why the electrons from valence band can easily switch over to the conduction band. So that is the reason their conductivity is high. And in case of semiconductor, now there is some kind of band gap. Okay, so when electrons are moving, they have to this energy gap they have to pass. Fine. And if it is insulator, now the band gap is very large, so it is really difficult for the electrons to jump to the conduction band starting from valence band. So this is the reason why conductor, semiconductor, insulator, all of them are behaving differently. Their electrical conductivity is completely different. Okay. First we will focus on conductors. What are the characteristics of conductors? So substances which conduct electricity through them to a greater extent, and this is the range we have already seen. Now they can conduct electricity through movement of electrons as well as ions, that is electrical conductivity or ionic conductivity. Okay, so metallic conductor belong to the former category, that is metallic conductor, silver, gold, copper, steel, all of them will be carrying this, that is they will be showing electrical conductivity because of the presence of free electrons. And if it is electrolyte, they will be conducting electricity through the movement of ions because they are electrolyte. For example, seawater. Seawater means there is NaCl, so it is acting as electrolyte. So two types of conductivity we can observe for conductors: electrical conductivity and ionic conductivity. Metals conduct electricity in solid as well as in molten state because they are conducting through electron, and electrons are always available, they are freely moving even in the solid state. So it is not necessary that the metals should be in molten state or in aqueous state. Okay, that is not the necessity. But if it is electrolyte, obviously the ions should move and it must be in molten state or in solution state. Okay, in conductors, the conduction band and valence band overlap with each other, that we have just seen, or you can say that the gap between them is very, very small. So there are free electrons in the conduction band always, and when we increase the temperature, conduction decreases. So this is very important characteristic for conductors, that how they are dependent on temperature. So with temperature, conduction is, the relationship is inverse. Temperature increased, conduction is decreased. And there is no effect of addition of impurities on the conductivity of conductors. So impurity defect we have already seen. Okay, so when we add impurity to these conductors, there is no effect of these impurities. So why we are mentioning it? Because you will see in case of semiconductor, when we add impurity, this is really creating a complete different scenario. Okay, but in this case, in case of conductors, they are already able to conduct electricity and there is no effect of impurity, and this point is very important. With temperature, conduction basically decreases. Okay, what about insulators? In case of insulators, we have seen that the conduction band, valence band, their distance between them is very high. So as a result, from the valence band they cannot jump to the conduction band. As a result, there is no free electrons in the conduction band. And remember, what is the relationship with temperature? There is no effect of change of temperature on the conductivity of insulators. Okay, so if we change the temperature, it doesn't matter anything. there is no effect of addition of impurities on the conductivity of insulators. Fine. So we can easily understand the difference we have seen in case of conductor. With temperature there is conductivity decreasing, but here there is no effect of change of temperature and there is no effect of addition of impurities. So this point, last point, is common for the conductor also, but not this point. Fine. Here we have some examples of insulators. They cannot conduct electricity. Semiconductor. So this is the range, and in semiconductor the energy gap between valence band and conduction band, compared to conductors obviously the gap is high, but compared to insulators the gap is small. So that is why they are in between, their behavior is in between conductor and insulator. The electrons of the valence bond can easily be excited to the conduction band because the gap is very small. And here, how is the temperature dependence? Now when we increase in the temperature, there will be increase in the conductivity of semiconductors. Okay. So basically, semiconductors are those solids which are perfect insulators at absolute zero. So at absolute zero, they behave as insulator, but conduct electricity at room temperature, because room temperature is greater than absolute zero. That is why room temperature is 25 degrees centigrade or 298 Kelvin. Fine, but absolute zero 273. So it is very less. So that means when we increasing the temperature from absolute zero up to room temperature, now as if the semiconductors, they are at first at absolute zero behaving as insulators, but now at room temperature they are conducting electricity. So temperature has huge effect on the semiconductors conductivity. There is an effect of addition of impurity on the conductivity of insulators. So this point is completely different from conductors, because also insulators, because in case of insulators and conductors we have seen there is no effect of addition of impurities, but in this case there is effect of addition of impurities. Now semiconductors, there are two types: intrinsic or pure semiconductor, that means there is no impurity, but in case of extrinsic semiconductor we add some impurity, and depending on whether the electrical conductivity it is through positive hole or negative hole, it will be p type or n type. Okay, so intrinsic is basically pure semiconductor, we are not adding any impurity, but in case of extrinsic semiconductor we are adding impurity. Now we will explore these two types. So intrinsic semiconductors, that is semiconductors because of thermal effect. So at 0 Kelvin, pure substance, that is silicon, absolute zero means 0 Kelvin. Okay, this is the minimum temperature that is possible. At 0 Kelvin, pure substance, that is silicon and germanium, they act as insulators. So we have already seen in the previous slide. Here we have already mentioned that they are those solids which are perfect insulator at absolute zero, that means 0 Kelvin, they are behaving as insulator. It is not okay, it is 0 Kelvin. Okay. 0 Kelvin, but they conduct electricity at room temperature. Room temperature means 298 Kelvin. Fine. So when it is 0 Kelvin, silicon and germanium, they are acting as insulators. Why? Because electrons, they are fixed in the covalent bonds and they are not available for conduction. Now when we are adding energy, that means we are increasing temperature, what is happening? When we are increasing temperature, some of the covalent bonds will be broken and the electrons will be released from these covalent bonds, and these electrons will be free to move in the crystal, and that is why they will conduct electric current. So here the semiconductor property we are getting, it is simply because of the thermal effect, because when we increasing the temperature, then only there are some free electrons and they are conducting electricity. But if we are not providing temperature, there is no, they are not behaving as semiconductors, they are behaving as insulators. Okay. What about extrinsic semiconductors? extrinsic semiconductors, from the name you can understand some external material should be present, that is impurity defect. So if we consider conductivity of intrinsic semiconductors that we are doing simply by increasing the temperature, it is actually very low to be of any practical use. So the value is so low that we cannot use it, we cannot apply it for any practical use. So that is the reason we are now adding some impurity to this pure silicon or germanium. The conductivity of pure silicon germanium very low at room temperature, that we have already seen, okay, when it is in pure state. But when we are adding, it can be increased by doping with impurities. Doping with impurities means simply addition of impurities. And when we are adding impurities, depending on the type of the impurities, there may be two types of semiconductors. One is p-type semiconductor, another one is n-type semiconductor. So it depends on what type of impurity we are adding, okay. So conductivity of pure silicon and germanium at 0 Kelvin, it is acting as insulator. Then when we are increasing the temperature up to room temperature, so from 0 Kelvin now it is at 298 Kelvin, now they are conducting electricity, but this value is very low. No, it is of no practical use. So that is why we are adding some impurity, and depending on the type of impurity, there may be two types of semiconductors. So p-type semiconductor. So silicon and germanium, these two examples we have already seen. So silicon, which is from group 14. So from the last digit, that is 4, we can understand that here valence electrons is basically 4. Okay, general electronic configuration of group 14 is NS2 NP2. So valence electrons number is 4. Group 14. So here we have 4 electrons surrounding silicon. Now we are adding boron to pure silicon crystal, and what it will do, there will be lack of 1 electron, because boron is from group 13. Group 13 means valence electron, the last digit, 3 valence electrons. So now instead of 4 valence electrons, we have 3 valence electrons, so there will be 1 hole. So when silicon is replaced by boron, if there are 4 bonds, if we consider this silicon, which is actual silicon, there are 4 electrons, but as it is forming bond with another silicon, so 4 more electrons are coming from the neighbor silicon atoms. So basically there are now total 8 electrons if it is silicon, but when there is impurity, then there are 7 electrons, because there is 1 hole, okay. So the absence of an electron in the hole means it is the presence of positive charge. That is why we call this doped material as p-type semiconductor. P for positive charge. Now when we are applying electric field, an electron from the neighboring position completely filled covalent bond, okay. So this is the position of the hole. Now suppose from the neighboring position another electron is coming to this hole. So now there will be new hole created at this position. In this way, the holes will be moving throughout the solid. So electron from neighboring completely filled covalent bond jumps into this hole, and a new hole will be created in the bond from which the electron has moved. So this is our new hole, okay. So this process will be repeated again and again, and the hole will move throughout the crystal. So because of this movement of the positive hole, there will be electrical conductivity. So the electrical conductivity is because of the movement of this hole, okay. So that is why we are calling it p-type semiconductor. So here silicon, in silicon we have added impurity from group 13. Now another possibility is there. Suppose if we add any impurity which is having 1 electron extra. That means now we will use group 15, because in group 15 valence electron is 5, because group 15 consider the last digit, valence electron 5. So let's see what happens when we add any impurity from group 15. So now again we have taken silicon. Surrounding silicon there are 4 electrons, and we have now taken phosphorus. Okay, this is P. So phosphorus 5 valence electron, it is from group 15, general electronic configuration NH2NP3. So now 1 electron extra. Adding phosphorus to pure silicon crystal results in a surplus electron, that is extra electron, and it becomes a free electron. So this is our free electron. So this free electron, the presence of this free electron, it means presence of negative charge, just as we have seen in the previous case, presence of positive charge, but now it is extra electron, extra negative charge. So that is the reason this doped material, or that is addition of impurity, after addition of impurity we call this doped material as N-type semiconductor. N means N for negative. So each atom of impurity leaves 1 free electron in the crystal. So if there is 1 phosphorus atom, there is 1 free electron extra. If there are 2, there will be 2 free electrons. So per phosphorus atom there will be 1 free electron. So due to this pentavalent doping, why we are calling it pentavalent? Because valency is now 5. Because of this pentavalent doping, number of free electron increases, and electrons are the major charge carriers in case of N-type semiconductor. So now the electrical conductivity, it is because of the movement of free electron, but in case of P-type, it is because of the movement of positive holes. So completely opposite scenario. Okay. Now here we have a problem. Classify each of the following as being either a P-type or N-type semiconductor. So here we have taken germanium, which is doped with indium. So germanium, it is from group 14. Indium, it is from group 13. That means 4 valence electron present here, but when we are adding indium, there will be 3 valence electron. That means 1 positive hole will be created in the first case. So this will be P-type. Similarly, when boron, which is from group 13, and now we are adding impurity silicon, which is from group 14. So here we have 3 valence electron, here we have 4 valence electron, so 1 electron extra. So this will be N-type, that is negative charge extra. So in this way we can easily find out whether it is a P-type or N-type. Simply first you have to understand whether that is from which group we have this element, and what is the group of the impurity that we are adding. Okay, so depending on there is extra electron or extra positive hole, we will have N-type and or P-type respectively. Non-stoichiometric cuprous oxide. So here we have cuprous oxide. Cuprous means copper having oxidation state +1. If it is cupric oxide, then it is CuO, oxidation state +2, but here it is +1. So cuprous oxide, here it is written non-stoichiometric. Cu2O, that means here the ratio of copper and oxygen, as we are seeing from this formula, it is 2:1, but actually it is not so, because it is non-stoichiometric. It can be prepared in the laboratory, and in this oxide, copper to oxygen ratio, it will be slightly less than 2:1. So if it is ideal structure, it will be 2:1 for Cu oxygen ratio, but as it is non-stoichiometric, it will be slightly lesser than this ratio. Account for the fact that this substance is a P-type semiconductor. Okay, that means positive hole will be there. So the ratio less than 2:1 in cuprous oxide, it means what? That some Cu+ ions have been replaced by cupric ions. So that is why the ratio is less. Now if we want to maintain the electrical neutrality, then every 2 copper plus 1 ion, that should be replaced by 1 Cu2 plus ion. That means when 2 Cu plus ion, suppose this is the original position of Cu plus, Cu plus. Now for these 2 when missing, and in their place now we have Cu2 plus. That means one site will be vacant. So when every 2 plus Cu plus ions replaced by 1 copper 2 plus ion, there will be creation of a hole. So in this way we can account for the fact that this substance, it will be p-type semiconductor. So conduction will be because of the presence of these positive holes, and hence it is a p-type semiconductor. So don't think that semiconductor means always you will have problem from group 13, 14 or 15. It may be this type also. This is completely different type, where copper it is from D block, it is not from P block. Okay, but as Cu plus, basically we have to see that which ion is replaced by which ion. So if the new ion it is having more positive charge, that means there will be extra positive holes, and if it is has more electrons, there will be extra electrons. Okay, so accordingly we will have p-type or n-type semiconductor. Magnetic properties of solids. So magnetic properties of solid, it may arise because of 2 types of motion. Fine. So one motion is electron, it can spin through its own axis. So suppose this is the electron and it is spinning toward this direction or the opposite direction. So as it is moving through its own axis, and there is negative charge in electron present. So a charged particle, when it is moving through its own axis, there will be generation of magnetic moment, and this is denoted by this type of arrow. And magnetic moment, that can also arise because of another type of motion, which is spinning electron. So electron, it moves around nucleus. This is nucleus. Okay. So if this is nucleus and electron is moving surrounding it, then also there will be generation of magnetic moment. Okay, so this is one type of motion, this is another type of motion, and both this motion you can see in this middle picture, both are present simultaneously. So this is the spinning electron, and this is actually spinning is this one, it is not orbiting, it is spinning. Okay, sorry for the mistake. It is spinning and it is orbiting. So here in the middle picture you can see this is the nucleus. The electron, it is spinning through its own axis, and when it is doing so, it is also orbiting around the nucleus. Fine. So 2 types of motion, 2 types of magnetic moment generation. So magnetic moment, as it is a vector quantity, the net magnetic moment of an electron, we can represent it by an arrow. So here arrow is used. Thus, a material may be considered to contain a number of magnetic dipoles, because in a material there are several electrons, each electron acting as magnetic dipole, so it will contain several magnetic dipoles, just like a bar magnet with north and south pole. So as if each electron is behaving as a bar magnet with north and south poles. And due to this magnetic moment of the electrons, different substances behave differently towards the external applied magnetic field. So now the electrons, they have their own magnetic moment, and when we are applying some external applied magnetic field, there will be different kinds of behavior.